All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. First of all, thank you guys for being flexible with me as I am taking basically just a work from home day. So how's everyone doing today? Hope you guys are doing good. Okay, so good. So some announcements. So probably most of you have probably seen online that the grades for the midterm are posted. So I just finished grading those literally just 45 minutes before the lecture. And so for most people, your grades should be online. I haven't graded all of them yet, just yet though, and so I can't post the solutions just yet. But for the ones that I have graded, I wanted to make sure that I put those online for you to see before the class. So I also don't have any information about the averages just yet, just because there's a few more that I still need to do. But I plan on having those done before Thursday for sure. But for the majority of the class, your grade should be online, and then I'll return the exams on Thursday for you to look at as well. Okay. Okay, so that's the information about the most recent midterm. Um, let's see. So I think I also mentioned in the email too that homework 4 has been posted. So make sure you check that out. So we're still covering a lot of stuff, and so the whole theme for homework 4 is 1D nonlinear programming methods. And so we're kind of right in the middle of it. So we've gone over one set of methods called elimination methods. And so today we're going to go over another set of methods called interpolation methods. And then probably on Thursday, we'll go over the last set, which is direct root methods. And so you should have everything you need after this week. But you should at least be able to get started on it, for now. Okay, and so that's all my announcements for today. Are there any questions I can answer before we get started with the lecture? Okay, all right, and so let's go ahead and get started. Okay. And so let's go ahead and pick up where we left off. And so if you recall from last Tuesday, we were going over nonlinear programming. Okay. We'll kind of refresh our memories on what that means in a second. And the topic for today is something called interpolation methods. Okay. And so, let's refresh our memory in terms of, what nonlinear programming is. Okay. So nonlinear programming is kind of a general framework for solving optimization problems. And the whole idea is to write algorithms or have approaches that don't rely on function derivatives. Okay. Okay. And so that's really key because even though we've seen that we have our kind of our classical methods that rely on function derivatives, sometimes it's just not possible to take function derivatives, for one reason or another, right? And so for some cases, we may have objective functions where the design variables don't show up explicitly in the function. Okay, so we talked about that last time. Or maybe you're optimizing the result of a finite element simulation. And so in that case, you don't have the variables in the function. Okay. Or maybe your function is just kind of too mathematically complex, where taking the derivative is kind of more cumbersome than not. Okay. So whatever the reason, it's very useful to have optimization methods that don't rely on derivatives. Okay. Okay, and so there's several different categories of algorithms that work under this framework. Okay, so we went over the kind of the first class of methods last Thursday. We called those elimination methods. And so the whole idea with interpolation methods, the approach is a little bit different, but it's still going to kind of have the same flavor as before. Okay. Okay, so the theme for today with interpolation methods is to make use of something called a surrogate function. Okay? And so what a surrogate function is that it's a representation of our objective function, but it's put in a way that is a lot more convenient to work with. Okay. Okay. And in particular, we want our surrogate function to have a couple main properties. Okay. And so first of all, the first property that we want for our surrogate function is that it has to contain our design variables in explicit form. Okay. And so even if our original objective function doesn't have the design variables explicitly within the objective function, we want our surrogate function to do that. Okay. And so we're going to have the freedom to do that because we can choose our surrogate function however we want. So that's the first thing. Okay. Because we have a lot of methods already that we can use when our design variables are explicitly in our objective function. Okay. And the number two property is that mathematically it should be something that's easier to work with. Okay. And so one way that we can kind of say this is that it's in a simple functional form. Okay. And so it should be, mathematically something that we can kind of easily, for instance, maybe easily take a derivative of. So maybe a quadratic function, maybe a cubic function, a linear function, maybe. Okay. And so it should be something that's relatively easy to work with. Okay. Okay. And so the whole idea is that you have kind of we can have kind of a very very complex optimization problem with an objective function that is either doesn't have the design variables or it has a complex form, but we're going to approximate it with something that has a simple form. Okay, so for example, let me just kind of visually, I guess not an example, just kind of visual kind of thing, right? So let's say that we have we're optimizing over a finite element simulation, just like last time. Okay. And so remember what we talked about that, usually when you have like a finite element optimization, let's say that you have your part here, you have its dimensions, so you have its length, maybe its diameter, okay? And so you want to optimize, you want to choose the best values for, the length and diameter, but, our objective function is, things that are that comprise the finite element results. Okay. Okay. Right. And so our objective function, it's still going to be a function of D and L, but maybe it doesn't, contain D and L exactly. Right. And so, it might be something like this. This is a very common objective function for a finite element simulation. Okay. So maybe you have the square root of something like maybe the maximum stress, in the bar squared divided by some reference stress. Okay. Plus maybe something with the deformation. So maybe like the max deformation divided by some reference squared. Okay. And so what we have in this is kind of a it's almost like a root mean square. That's basically kind of the idea. And so you take each quantity that you're interested in, you normalize it, you square it, and then you square root it to make sure all the units are the same. Okay. Okay. So that's what it would be like if you were to try to run this optimization just straight up without any kind of methods, right? And so with the interpolation method, and so here, instead of representing the system like this, we're instead going to form a surrogate function. Okay. Okay. So actually, let me give this a different name. And so instead of f of d and l, so f of d and l is kind of the original objective function. And let me call this f bar. And so the f bar will kind of indicate this is a surrogate for that. Okay. Okay. So maybe we have something like a d squared plus b l squared plus a d plus or excuse me, should be a different variable here, plus cd plus little dl plus e. Okay. Right. And so this that I've just boxed is a representation of the one on below. Okay. And so it may not be exact, right? And so who's to say the relationship between stress and deformation in a bar is a quadratic relationship with the diameter, right? We don't really know that. But what we can do is we can choose the values of these coefficients. Okay, so we have a, little b, little c, little d, little e. Okay. We can choose the values for those coefficients so that the surrogate function tries to closely mimic or closely resemble our original objective function as closely as possible, at least within a certain range. Okay. Okay. And so the reason I kind of add that caveat within a specific range is that it's normally very difficult to get a quadratic function or a function of any kind of fixed form to match an arbitrary function over a long period of time. But usually for a kind of a small area, a confined area, you can get the function to look very similar to a quadratic. Okay. Okay. So that's the idea. So that's kind of our goal with this unit is to, use the surrogate function because, now that we have the surrogate function, it's just a simple quadratic function. And so this is something that we can take a derivative of and kind of find our optima or find our extrema in kind of the classical way And this is something that's kind of relatively easy to do with the quadratic function. Okay. And so we're going to spend a lot of time today talking about, how do we actually get the surrogate function, how that's formed, and then we'll do an example later today to see how we can actually use this in an optimization. Okay. All right. Any questions on this so far? Okay. All right. So that's kind of where we're going for today. Okay. And so, like I mentioned, there are lots of different types of surrogate functions that you can choose. And each one kind of has its own pros and cons of each. We're going to go with kind of the simplest one that we can do in this situation, which is a quadratic surrogate function. And so this method of using a quadratic surrogate function to optimize an objective function is known as quadratic interpolation. Okay. And so a quadratic surrogate function, and so I'm going to kind of go back to 1D for now. A quadratic surrogate function would kind of look like the following. So if f of x is equal to ax squared plus bx plus c, okay, where of course little a, little b, and little c are unknown coefficients, and so that's something we're going to solve for. Okay. And so the kind of the graph of a quadratic function looks something like this. Okay. This is x. This right here is f of x. I should say f bar of x. Okay. Okay. So we have 3 degrees of freedom here. And so, we have 3 unknown coefficients, a, b, and c. Okay. The reason we use a quadratic surrogate function and, and we don't use a linear function or anything like that is that quadratic is the lowest order polynomial that you can have that has a clearly defined local minima, which is also its global minima. Okay. We can't use a linear function because a linear function has no extrema, right? And so a linear function just has a straight line all throughout. Okay. And so if we wanted to get kind of a local minima, then we have to use a quadratic function, right? And so that's kind of the lowest that we can go. There's higher order interpolation methods. There's cubic interpolation. And if you were able to find the textbook, you'll see that there's a big section on cubic interpolation. We're not going to go there just because it kind of gets, the calculations kind of get cumbersome a little bit. But that is there and available for you. Okay. Okay. And so, just like we mentioned above, this surrogate function that we have here, okay, we're going to use it to approximate the original objective function. Okay. And the key word here is approximate, right? And so, and unless your objective function is a quadratic function just kind of by itself, it's going to be really difficult for you to get kind of perfect matching between the surrogate function and the original objective function. Okay. And so the idea is to not match it exactly or not match it, as closely as we can. We are making an approximation, but the hope is that that approximation is good enough to find the optimum. Okay. And so in reality, you might have a graph that looks like this. And I think the example that we're going to do today looks like this as well. Okay. Okay, and so if you have kind of a typical graph here of x and f of x, let's say that we have our original objective function, maybe it looks something like this. Okay. Okay. And then our surrogate function, so this original objective function actually looks pretty quadratic already because it kind of has that parabolic shape. Okay. But maybe when we go to find our surrogate function, it may look something like this. Right, and so it may not be a perfect match, but we at least we can see here that the minimum are at least somewhat close, right? And so the minimum for this function, maybe the original objective function may be here, and the minimum for the surrogate function may be somewhere like there. Okay, so they're not quite matching, but they're close enough. But what we'll learn later on today as well is that once you have a surrogate function, you can actually refine it so that it becomes a more accurate representation, a more accurate approximation. Okay. Okay. Any questions on this before we jump into a quick sample? Okay. All right. So that's the idea, right? And so we instead of working with the original objective function, which has maybe unknown mathematical structure and may not even have the design variables in it, we're instead going to approximate it with something with a known mathematical structure and that has that has the design variables explicitly in it. Okay, because we already know how to handle such situations. And so the next question is, how do we actually find or how do we actually determine what our surrogate function needs to be? Okay. Okay. And so to compute a surrogate function, what you need to do essentially is you need to compute the values of all of the unknown coefficients. So the values of little a, little b, and little c. Okay. Because the values for x there, if these in that functional form are more or less fixed, right? And so we know our quadratic function has to have a quadratic term x squared, it has to have a linear term x, and it has to have a constant term c. Okay. And so the question is, now that we know what we need to do to define our surrogate function, how do we actually go about doing this? Okay. All right. And so the way we actually do this is through objective function evaluations, right? So very much in the theme of nonlinear programming. Okay. And so let's do an example to kind of show you what that means. And so essentially what we're going to do is that once you evaluate the objective function 3 times at 3 known values for x, then what you're going to have is basically a system of equations to solve for our 3 unknown coefficients, right? So you're going to have 3 equations and 3 unknowns. Okay, so let's jump into an example. Okay, and so for this example, let's say that we have this function and we want to approximate it with a surrogate function. Okay. So let's say our original objective function in this case is f of x is equal to x raised to the 6th power minus 9x cubed plus 2x squared minus 11. Okay. Okay. And we want to represent this with a quadratic surrogate. So we're going to have f bar of x is equal to ax squared plus bx plus c. Okay. And so we want to find the values of a, b, and c. Okay. All right, so let's evaluate our original objective function at 3 different values for x. Okay. Okay. And so my selections for the values for x here are going to seem somewhat arbitrary for now, but you'll see that it'll have some significance later once we're solving optimization problems. Okay. And so first we're going to try x is equal to 0. Then we'll do x is equal to 1. And then x is equal to 2. Okay. Okay. And so let's go ahead and do that. And so for step 1 here, we're going to evaluate everything at x is equal to 0. Okay. So we're going to plug in 0 into our original objective function. So we have 0 raised to the 6th power minus 9 times 0 cubed plus 2 times 0 squared minus 11. Okay. All right. So once you plug everything into this, everything with 0 is going to cancel out. And so we get minus 11. Okay. And then what we're going to say here is that, this right here is equal to our surrogate function evaluated at the same values for x. Okay. Okay. And so let's plug in our surrogate function here. So we have f bar of x. Okay. Or I should say f bar of 0 because we're plugging in 0 in for x. Okay. This is going to be a times 0 squared plus b times 0 plus c. Okay. Okay. So that's our first equation, although this first equation is kind of trivially solved because we just plug in x for 0. And so we're going to do the same thing for point 2. So for point 2, we're going to plug in x is equal to 1. All right, so we have 1 raised to the 6th power minus 9 times 1 cubed plus 2 times 1 squared minus 11. Okay. And so you plug that in, what do we get? 1 minus 8 plus 2 minus 6. This is equal to minus 17. Okay. And so this is going to be equal to our surrogate function, again, evaluated at x is equal to 1. Okay. So you have a times 1 squared plus b times 1 plus c. Okay. So let me just go ahead and box these equations just so that you kind of know. Right. Okay. And then we're going to do the same thing at our last point here. So you have f of 2 is equal to 2 raised to the 6th power minus 9 times 2 cubed plus 2 times 2 squared minus 11. Okay. All right, we plug this in. And what do we get from this? And so this is way too much math to do in my head. So in our notes here, we can see that this is equal to minus 11 as well. Okay. And then we're going to plug this into our surrogate function. So we have a times 2 squared plus b times 2 plus c. Okay. And so what I have, everything that I've boxed here is our system of equations. So we have three equations for the three unknowns, okay? And so in theory, you'd be able to solve these three equations for little a, little b, and little c. Okay? We're not going to go through that, just because, I think that that's just going to end up taking time. But the details for that are outlined in the um, lecture notes. Okay. Okay, and so if we do that, let's go ahead and see what these are. And so if we do that, we plug in everything, we get A is equal to 6. B here is equal to -12, and C is equal to -11 from the first equation. Okay, and so we plug all those in, we get f bar of x is equal to 6x squared minus 12x minus 11. Okay. And of course, just like we like to do in this class, let's go ahead and plot these. And so I'm going to plot our surrogate function as well as our original objective function. Okay. And so let me start with the surrogate function. And so the surrogate function is kind of a nice quadratic polynomial. And so we have kind of a nice parabola like that. Okay. So that's our surrogate function. And then our original here, our original here happens to also be a polynomial, but it's a sixth order polynomial. So actually the matching is actually not that great. So it looks kind of something like this. And so in purple here, we have our original function. Okay. All right. And so, the point of this example is to kind of show you that, you can form these surrogate functions and you don't really need anything fancy with it, except for maybe a lot of patience with algebra. That's probably the most important thing. Okay. Okay. And that's why this is kind of an attractive method for nonlinear programming, right? And so nonlinear programming, basically any algorithm that relies just on function evaluations is going to be, popular for that reason. Okay. Okay. Any questions on this? Okay. All right. And so now that we've kind of introduced the idea of surrogate functions and how to find them, let's talk a little bit about how we can actually use these in optimization. Okay. Okay. Right. And so let's start by kind of stating the fact that, because we have kind of a very simple quadratic form, we can find the minimum of this quadratic function fairly easily. Okay. And since it has such a simple form, and since we have just kind of a 1D problem, we can do so, just using our classical methods. And so taking the derivatives. And so if our f bar here of x is equal to ax squared plus b plus x plus c, okay? If we take the derivative of our original function here, then we get 2ax plus b, okay? And of course, we're going to set it equal to 0, okay? And so if we solve for x, okay, because that value of x there is going to be the minimum of our function. And so x here is going to be minus b divided by 2a. And so as long as we can find our surrogate function, finding its minimum is actually going to be quite easy, okay? And in fact, the fact that we're using a quadratic function here, it's very easy to determine or very easy to verify that this is in fact a minimum of the function, okay? Because if we take one more derivative here, right? In order for this to be a minimum, we should get a positive number when we plug in this value for x min, okay? But in fact, we don't even have to worry about that because if we take one more derivative, we end up with a constant. Okay? And so what this is telling us is that as long as the only way that this term here can go negative is if a is negative, right? And so as long as a is greater than 0, then our surrogate function will have a minimum with the value that's given above. Okay. And so that means that if we can find the values for a, b, and c, kind of easily, then we can find this that one. Okay. Okay. And so how do we determine the values for a, b, and c? Okay. And so traditionally, we would basically follow the same process that we followed in the previous example, right? But we can streamline that process. And so, you don't have to kind of go through this trouble of setting up a system of equations and things like that. Okay. We can kind of do so, more, we have formulas for that, in other words. Okay. Okay. And so for these formulas, let's go ahead and assume I made a little bit of a blunder kind of up to this point. And so I kind of swapped the positions for A and B. And so I'm gonna give a new form for the surrogate function here, just so that my formulas here are kind of consistent with the notes. Okay. And so let's say assuming our surrogate function. I apologize for this. I didn't realize it until I was writing the last section that my coefficients were not consistent with the notes. Okay. And so let's have our f bar is equal to, okay, instead of having the a be the x squared term, we have a just be the constant term. Okay, so we have a plus bx plus cx squared. Okay. And that means x min here is going to be a minus b over 2c. Okay. Right, and so that's so it's a slight change in notation. So I basically swapped the positions of a and b, and so a is now the constant term and c is the quadratic term. Okay. Okay. Let's also assume that we've evaluated our original objective function at 3 locations. So we'll call them XA, XB, and XC. Okay. Those are capital letters to kind of differentiate them from the coefficients in our surrogate function. Okay. So we'll assume that XA is equal to 0, XB is equal to T, and XC is equal to 2T. Okay. Where T here, T is what's called the step length. Okay. And so in our previous example, you use a step length of 1, essentially. Okay. Okay. And so once we evaluate our objective function at these 3 locations, we're going to have 3 function values. Okay, so we'll call those FA, FB, and FC. Okay, where FA is our original objective function evaluated at XA, FB is our original objective function evaluated at XB, and FC is our original objective function evaluated at XC. Okay, so those are the 3 variables that we have to play with. Okay. All right. And so if we evaluate our surrogate function at the same points, we actually can get formulas for A, B, and little a, little b, and little c. Okay. Okay. We have x bar, xa, f bar of xb, f bar of xc. Okay. And so you don't actually have to do this, okay? But I'm just kind of explaining it here just so that you can kind of see where these formulas come from, okay? Because just like the previous example, doing so is going to give you a system of 3 equations for our 3 unknowns, okay? Our unknowns being little a, little b, and little c, okay? And so solving this system, okay, solving this system will yield us kind of the following equations for little a, little b, and little c. And so we're actually helped a lot by the fact that XA here is assumed to be 0. And so anything involving XA would just kind of 0 out, which kind of simplifies things a lot. Okay. Okay, so we'll start with the value for little a. So remember, in our revised form here, little a is the constant term. Okay, so little a here is just simply going to be FA. Okay, and so FA, remember, is our original objective function evaluated at x is equal to 0. Okay. Okay, we have little b. So little b is a little bit more complicated. And so we have 4 times FB minus 3 times FA minus FC. Okay, all this is going to be divided by 2t. Okay. And then we have the value for c, which is FC plus FA minus 2FB divided by 2t squared. Okay. Okay. And so, once you determine a value for t, which, we're going to talk about soon after this too, you can use these formulas here to determine the values for little a, little b, and little c. Okay. Things get a little bit more complicated when xa is not equal to 0, but we'll go through that during the example. And so let me just kind of make this caveat here. So these formulas assume xa is equal to 0. Okay. And so that's not going to be necessarily the case in the future. Okay. And they also kind of assume that all the points are kind of equally spaced apart. But for now, these, because once you kind of lift those restrictions, it gets a little bit crazy, kind of what the formulas are. But and so we'll just kind of rely on this for now. Okay. Okay. Any questions on any of this so far? Okay. All right. And so these are our values for x, for little a, little b, and little c. Okay. Okay. All right. So this is fine. This is good. Okay. But it's we can't just kind of blindly go in and use this kind of these formulas here. Okay. Because the key to using this formulas is to select an appropriate step size. So select the appropriate t. Okay. So I know it's a lot of information. So this is very similar, very similar to the simplex method, right? Where we talked a lot about kind of a lot of special rules, a lot of many things to consider. And so unfortunately, just that's just kind of the nature of a lot of these algorithms, that there's a lot of kind of special rules, there's a lot of kind of considerations to make, a lot of kind of special cases. And I think that's kind of what makes optimization really challenging, is that there's just so many things you have to kind of keep in mind, and you have to, but at the same time, you kind of have to follow a strict kind of logical sequence of steps in order to arrive at the right solution. Okay. So I'm going over these kind of very carefully right now, just because I think we're still kind of getting used to algorithms and kind of their way of thinking. But just from here on out, it's going to be kind of a steady diet of this. But the good news is that for the most part, at least for anything practical, you wouldn't have to kind of implement these, or you wouldn't have to solve these out by hand yourself. Your challenge is going to be how do you write computer code to kind of mimic these same things. Okay. But in order to write good computer code, you have to kind of intuitively yourself kind of understand what's going on with the algorithm. And so that's why we're kind of going through right now, we're kind of going really slow, to kind of understand every single step that we're taking. Okay. Okay. All right. So how do we select the appropriate step size for t? Okay. And so we want to choose the value for t. Okay. We want to choose our step size such that the minimum of our objective function lies within the range of 0 to 2t. Okay. Okay. And so, because, and because our surrogate function kind of has a quadratic form, this, we can kind of boil this down into three kind of situations. So, you're either going to have a situation that, and so you're going to start, most times these start by you kind of guessing a step size yourself, right? And so what you're going to do is you're going to guess a step size. You're going to check the relative values of the function evaluations. And then based on that, you can either make a decision to refine your step size, make it smaller, or expand the step size to make the step size bigger. Okay. Okay. So let's go over kind of the three scenarios of what you can do. Okay. Okay. And so the first scenario, so let's say that FB, which is f of t, is greater than FA. Okay. Right. And so if this is the case, then our minimum is kind of somewhere in the, it happened kind of early. Okay. And so what you can kind of say is that in this case, our minimum is somewhere in between our range here, but it happens so early that we're kind of doing a lot of kind of wasted steps. Okay. Okay. Because we want to make sure that we kind of get, as many function evaluations in that minimum as possible. Okay. Because, if we have the situation where our second function evaluation is greater than our first one, and we know the fact that our surrogate function has a quadratic form, it looks kind of something like this. And so, maybe we have something that looks like this. Okay. And so let's say that FA is right here. Okay. FA is always going to be at x is equal to 0. Okay. Then maybe our FB is somewhere here. Okay. Where this right here is x is equal to t. Okay. And this right here is FC. Remember, FC is evaluated at x is equal to 2t. Okay. All right. And so you can see just based on these lines here, FB is greater than FA. Okay. And so that means that our function, our parabola, reached a minimum, and then it was on the upswing after that. Okay. And so it's going up from there. And so in this case, we kind of, our step size is a little bit too big. And so we should make our step size smaller. Okay. Because a better way to do this, and let me use kind of an orange here. Okay. Okay. And so if we keep the same location as FB, but we instead turn this into FC, okay, that means FB is going to be somewhere in the middle here. Okay. That's a much better way to capture that minimum there because we kind of we made our window small enough so that our minimum kind of occurs in the middle of the domain, whereas before it was kind of far. So technically, if your step size is too big, it could work. It's just that you might just do a lot of kind of extra work on the back end because your initial approximation was not that good. Okay. Okay. So this is the first case, and so if your second function evaluation is greater than the first, you need to make it smaller. Oops. Okay. And in fact, the most common thing to do is just to cut the step size in half. Okay. Okay, number 2. And so the second case is, let's say that our second function evaluation is less than our first one. Okay, so if FB is less than FA, okay, right? But, or not but, and FC is greater than FB, okay? And so visually, this looks something like this. And so let's say that we have our function here. We have f, x. We have our surrogate function. Okay. We have our parabola. Okay. FA is always going to be at x is equal to 0. Maybe FB is right here. and FC is up there. Okay. FB doesn't have to be at the minimum, and in fact, most of the time it's not going to be at the minimum, but it should be less than FA. Okay. All right. And so in this case, we kind of have the perfect, this kind of the perfect surrogate here. And so in this case, our step size is perfect, and we can go ahead and move on to the next step in the algorithm. Okay. And so this is the best case scenario, and this is kind of where we kind of hope to start off with every quadratic interpolation problem. Okay. Okay. Number 3. And so the process of elimination, this is the case when we need to increase our step size. Okay. And this occurs when you have kind of a monotonically decreasing values for f at each successive, at each successive step. Okay. All right. And so in this case, we have FC, or I should say if FC. Okay. And so if FC is less than FB, which is also less than FA. Okay. And so if this is the case, then our step size by itself is too small. And so in fact, this is the worst case because we can't say, or we have no idea if our function minimum is actually within this range here. Okay. And so visually, it looks something like this. X, we have f bar of x. Okay. We have a parabola. FA is always at the 0. Okay. Okay. And so a situation like this is that if you have 3 consecutive points and they're all kind of in that kind of downswing of the parabola. Okay. And so we haven't quite hit the minimum. The minimum's not within kind of our range for our surrogate. Okay. And so if this is the case here, we need to make our step size bigger. Okay. We need to make it bigger to make sure that we actually capture that that location of that minimum. Okay. Okay. And so the first step in a quadratic interpolation optimization is to find kind of the appropriate step length. Okay. And so you're going to run various tests, and so you're going to evaluate the function at different locations until you get basically situation 2. Okay. And I think that'll probably be the last thing that we do today. And so I'm not quite done yet explaining all the details of the algorithm, but I think we have enough to at least start the example. And so I think what I'll do for the rest of class today is we'll start the example. We'll kind of progress to a certain point. And then once we get to the point where we need to kind of explain the rest of it, we'll go ahead and call it there. And then we'll explain the rest of the algorithm on Thursday. Okay. Okay, but any questions on these 3 scenarios here? Okay. All right. So let's go ahead and jump into an example, and then and then we'll continue this and finish it up on Thursday. Okay. Okay. So in this example, let's find the minimum of the following functions. Function. Okay. F of x is equal to x to the 5th minus 5x cubed minus 20x plus 5. Okay. And so let's use quadratic interpolation. And let's at first try a step size of 0.5. We're not going to end up at 0.5, but we have to kind of start somewhere. And so let's set our initial t at 0.5. Okay. Okay. So maybe not the best example here, because I've kind of been preaching this entire time that we mainly use nonlinear programming for cases where we can't take the derivative. In this case, our original objective function, we can take derivatives, right? And so it's just a fifth order polynomial. And so taking the derivatives of this is not that bad. But I'm doing this case just for kind of illustration purposes. But in reality, you'd probably use something different. Okay. So let me go ahead and circle this. And so we'll call this our original objective function. Function. Okay. All right, and so let's go ahead and start the quadratic interpolation algorithm. And so the first step, and so I call this step 0, is to find an appropriate step length, because that's something that's going to be important for the rest of the thing. Okay. Okay. And so what we're going to do is we're going to use our 3 kind of criteria from above and evaluate our original objective function at various points. And then we're going to wait and see until we find a value for t that gets us into situation 2 above. Okay. Okay. And so just a reminder, what we want to get is we want to make sure that FB is less than FA. Okay. And so our second function evaluation should be less than our original one, but FC should be greater than FA. Okay. All right. So that's what we're hoping to get. Stop biting my wire, you little shit. My cat is next to me and he's trying to bite my charging cable. Okay. All right, and so let's start evaluating our original objective function at various points. Okay. Okay, so remember we're starting with an initial step size of 0.5. So let's go with that. So let's evaluate f at 0. We'll evaluate f at 0.5. Okay. Because remember we want to fb is our function evaluation at xb. And then we're going to evaluate our function at x is equal to 1 too, because 1 is going to be 2t in this case. Okay. Okay. And so if we do that, we get f0 here. We plug in 0, we get an f value of 5. Okay. We plug in 0.5, we get 0. We plug in 0.5, we get an f value of minus 5.6. Okay. And then we plug in a value for x is equal to 1. We get f is equal to minus 19. Okay. Right. So this here, f0, this is fa. F of t, this is fb. And f at 1 here, this is fc. Okay. And so these values can be negative too. And so there's no restrictions on positive or negative here. Okay. Right. And so based on these values, we can say that FA is greater than FB, which is also greater than FC. Okay. So our function is kind of monotonically decreasing from XA to XB to XC. Okay. So this right here is situation 3 from above. And so in order for us to find the appropriate step length, we need to make our step size bigger. because we haven't quite found the minimum yet, or the minimum is not within our, you know, not within our range just yet. Okay. Okay. And so, technically speaking, when you make the step size bigger, you can make it bigger by any amount. Okay. But the most convenient thing is to actually increase it by 2. Okay. And so we're going to try a step size of 1.0 as opposed to 0.5. Okay. Okay. And so with the step size of 1.0, we're going to need f of 0, we're going to need f of 1, and we're going to need f of 2. Okay. So this is double original. Okay. All right, and hopefully you can kind of see why, because you can see here that we have 2 of these pieces of information already. And so we have f of 0 from before. F of 0 is equal to 5. Okay. F of 1 we actually evaluated in the previous step as well. We know that this is minus 19. Okay. So these 2 here are from previous step. And so we can just copy those over. And so, for the lazy mathematician like myself, this is perfect. We only have to do one new function evaluation. Okay. And so if we evaluate the function at x is equal to 2, that is the new one. And so that's going to be minus 43. Okay. All right. And so let's check the relative magnitudes of these terms here. Because we know that, f of 2 here, this is fc. This is fb. This is still fa. Okay. From this, we still see that fa is greater than fb, greater than fc. Okay. And so since we have the same situation as before, let's make our step size bigger once again. Okay. All right, so let's try one more. Okay. I'm just going to double it again, just because just so that we can use our f of 0 and f of 2 from before. Okay. Okay. So let's try f of t. Let's try t is equal to 2. And so from that we have f of 0, f of 2, and f of 4. Okay. So let's go ahead and reuse the values for f of 0 and f of 2 from the previous step. So that's going to be 5 and minus 43. Okay. And so if we evaluate f of 4 in this case, then we get 629. Okay. All right. And so in this case, we have fb, which is less than fa, and fc is greater than fa. Okay. And so this puts us in situation 2. Okay. And so that's good. So that means we found our kind of optimal step length or appropriate step length. And so that we can now proceed with the rest of the algorithm. Okay. Okay. All right. And so knowing this information, knowing that now that we've kind of found kind of the appropriate step length, what we can say is that our minimum, or the minimum for our surrogate function, is going to be somewhere between 0 and 4. Okay. So we've kind of significantly narrowed down our search, our search kind of domain, right? And so now we can kind of continue from here with the rest of the algorithm of finding the coefficients, plugging them into our surrogate, finding the minimum, and then going from there. Okay. All right. Any questions on any of this? Hopefully that makes sense in terms of why we kind of go through this exercise of finding the appropriate step length. The algorithm would still kind of work if you did it otherwise. It's just it'll kind of be a bit more painful. And so this and that's the thing about algorithms, that a lot of times it seems like you're kind of doing a lot of painful math, a lot of painful programming, but these algorithms, at least all the ones that we are working on, have already kind of been developed, and so you can have faith that if some steps and some calculations might seem annoying, but it's actually going to be more trouble if you don't do these steps. Okay, or you could just get the wrong answer, which is also not right too. Okay. Okay. So we have about 4 minutes left, and so we don't have enough time to go to the next step. But let me give you a little bit of a sneak preview, just so that we can kind of hit the ground running on Thursday. Okay. Okay. So with this step length, okay, and the corresponding values for FA, FB, and FC. Okay. We have all the information that we need to form our surrogate function. Okay. And then as a reminder, forming our surrogate function means solving for the values for little a, little b, and little c. Okay. Okay. Right. And so we went over the formulas for that, earlier in the lecture today. Okay. And then based on the values for little a, little b, and little c, we can then find the minimum of our surrogate function. Okay. Because our surrogate function, we know, has a simple quadratic form. And so, if we plug in the values for little a, little b, little c, we can find the minimum of that function, without any problem. Okay. Okay, so all that sounds good, right? Let me remind you that, this surrogate function that we're using is not our actual objective function, right? It's a representation, or it's an approximation, okay? And so the next question that we have to ask ourselves is that, with these coefficients and with these function values, is the surrogate, or maybe our approximation for the surrogate minimum, is that a good approximation for the original objective function? Okay. Okay. Sometimes it is. Sometimes it is a good approximation, and you can just stop right here, right? And so the algorithm ends early. But kind of more times than not, you're going to have to kind of improve the surrogate, or what we say, kind of refine the surrogate, so that your approximation is better. Okay, and so that's kind of where this algorithm starts to iterate. Okay, and so this here is step 0. And so next time on Thursday, we'll talk about how do we actually iterate on this, improve the surrogate, and then improve our approximation for the minimum. Okay. All right. Any final questions on this before we wrap it up for today? All right. Question. So in the last example, what did I mean by or did I mean to write FC is greater than FB? Yes. Thank you. Yeah. So this should be FC is greater than FB. Thank you. Okay. Yeah, FC. Yeah, as long as FC is greater than FB, then that means that we've already hit the minimum and we're kind of on the upswing. So yeah, thanks for catching that. Okay. All right. Any other questions on this? All right, so that's all we got for today. So on Thursday, I'll be back in class, and in fact, I'll bring the exams on Thursday. And so, if you want to pick up your exam, I'll have them in class on Thursday. If not, I'll bring them to the next class next Tuesday, and it'll be in my office. Okay. All right. So thank you guys again for your flexibility today. Thank you guys for meeting online, and I hope you guys enjoy the rest of your day.